Welcome back to closures for the normal force, and in what we will do in the next 8 minutes, we will discuss the so-called elastoplastic closure models for the normal force. Again, you see these two particles approaching each other. We have this normal overlap, and in the core of these elastoplastic models, we just have a single spring element to calculate the force. The big difference to the previously discussed force model is that this spring stiffness is not constant and depends on whether we have a loading, denoted here with the superscript L, a loading phase, or an unloading phase, denoted here with a superscript U. As before, we are interested on the normal forces on particle I and particle J, and as before, those forces are the same, with the only exception being the sign here. In the group of elastoplastic force closure models, we have an important subgroup being the hysteretic elastic force closures. Okay, here denoted as Fn superscript hys. Here we just use a different spring stiffness for the loading and the unloading phase to calculate this hysteretic elastic force. And this is already able and enough to simulate plastic deformation of the contacting particles or the particle wall contact. Important, we generate here the energy dissipation due to differences in this spring stiffness. So please note that even without a viscous damping element, we can simulate here energy dissipation. You will see that a surprisingly simple expression results for the coefficient of restitution. Let us now have a look at the mathematical expression to calculate this hysteretic force. As already mentioned before, we have to differentiate between a loading phase and an unloading phase. For the loading phase, which is characterized by delta n dot larger than 0, we use a loading spring stiffness. The loading spring stiffness here is denoted as KNL, and we use this spring stiffness simply multiplied by the normal overlap to calculate this normal force. If we are in the unloading phase, so delta n dot smaller than 0, this is the case if the particles separate from each other, have a positive relative normal velocity. We use a similar expression. However, now we use an unloading spring stiffness Kn superscript U multiplied by this difference of the current normal overlap and a residual normal overlap. You will see on the next slide why this must be the case. Important for you is that again we have here a linear combination between the spring stiffness and this overlap. For the case when this overlap delta n is very small and we have a separation of the two particles or the particle and the wall, we set this force simply to 0. Why this is the case, I will show you on the next slide. The coefficient of restitution for this specific force closure can be very simply calculated from the square root of the ratio of these two spring stiffnesses for the loading phase and the unloading phase. I have avoided to put in all the equations for this calculation of the coefficient of restitution on this video. However, you find these derivations in the supplementary material, specifically in this PowerPoint presentation. The hysteretic elastic force closure shown here is a purely repulsive, non-cohesive contact force model variant. Please note that from the group of hysteretic elastic force models, other variants exist that can be cohesive and that can also have attractive forces. For further details, more models, more force closures, please see these publications of Luding, or Voskrin and Sarkar also discuss these more advanced hysteretic elastic force models here. Having now said enough and having looked enough at equations, let us now have a look at a graphical illustration of this specific type of elastoplastic force closure. Here you see a plot of the normal contact force, the magnitude of that force, versus the normal overlap. Let us first assume that the two particles are about to contact at point A here. Okay. Now the particles move towards each other. There is a positive relative velocity. The particles move towards each other. This delta n prime, as shown here on the next slide, would be larger than 0. The particles would approach each other, right? For this phase, we use this loading stiffness Kn superscript L, as indicated here by this line going from A to B, right? The overlap is increasing with time, and here we use the loading stiffness. This is very similar to what we have in the linear spring dashpot element, with the exception, of course, that we don't have a dashpot element. Now let us consider the particles have arrived at their maximum overlap, delta n max, where they experience the maximum normal force, which of course is repulsive, right? And now move away from each other. Now this delta n dot would be smaller than 0. It would be negative, indicating a relative velocity of the particles that leads to separation, right? What we would do now is we would go along this line here from B to C and model that the normal force drops. Okay, the dropping here is more extreme. The slope of this curve is larger than this slope, indicating that this stiffness Kn superscript U is larger than this stiffness here. To get the force from this line, from this point B to C, we need to take into account this residual overlap, delta n res, which is related to the maximum overlap, delta n max. The relation is simply that we take into account the trigonometric relationships in this triangle here. Important for you is that, of course, we need to know this delta n residual or the delta n max, because otherwise we cannot calculate this branch here. If you're then at force 0, we would like to bound, of course, the force to 0, and that's why we set the hysteretic force here to 0 if the overlap is less than this delta n residual. I mentioned before that this hysteretic force model can model dissipation of energy. When we think about the energy that is essentially stored in the contact, it is the area below the lines A to B and this point here. If you think about the energy that is released in the unloading phase, it's simply the area below this curve here, this connection between B, C and this point here. So the energy that is dissipated in such a contact is simply the remaining area, the difference between those two areas, and is the area here in red. Again, if you want to go through the derivation of this, you find everything in the supplementary material. Finally, I would like to stress again that for each contact between particles or a particle and a wall, we must save the information on this maximum overlap delta n max or the residual overlap delta n res. And this requires simply more memory in our computations. Summing up, the shown hysteretic elastic force model here requires a little bit more of memory. However, it doesn't need a dashboard element for energy dissipation. It instead models that by changing the stiffness. This has the advantage that we don't need to bound this normal force as in the case of the linear spring dashboard element model, but we can by construction consider a perfectly repulsive force. Same as the linear spring dashboard element model, this hysteretic force model is linear in the overlap, meaning that it's computationally very efficient. With that, I would like to close. I hope you enjoyed it. See you next time.